Our next spreadsheet is going to be a spreadsheet in which we are going to solve some of our column problems. Now, this one is set up a little bit differently than the previous spreadsheets in that we are going to have multiple sheets on this one file. As we look at the bottom, you'll notice that there's a number of tabs. The first tab that's open here is the first sheet that opens up, and you'll notice that I named it slenderness ratio. The next one is Euler's column. The next one is intermediate structural steel. And then the last one is intermediate machine design. Now, how I formatted this was to start on the slenderness ratio page, or the slenderness ratio sheet as they're called in Excel, where we can then determine from this sheet which one of the tabs we're going to be going to on the bottom. We know that when we have column problems, the slenderness ratio has to be greater than 100 in order for it to qualify as a long column or an Euler's column, to use those equations to calculate the critical force that will buckle the column. If that value is equal to or less than 100, it becomes an intermediate column, which then we just need to decide, depending on the information that we have, is it a structural or a machine design application, which we see on the bottom here. So on the first page here, I started with the slenderness ratio inputs. The equation for the slenderness ratio can be found in the handouts from the column unit. So if we go to the camera here, the second page of the column handouts gives us our equation for the slenderness ratio. That is going to be K, which is the K factor based on the end conditions, times the overall length divided by the radius of gyration. Now, the radius of gyration can be calculated using the moment of inertia divided by the area and then taking the square root of that. We compare that number to 100. If it's greater than 100, it's a long column. If it's equal to or less than 100, it becomes an intermediate. So on that first sheet, I'm using this equation. Now, to put that into an Excel format, remember, we have to fit that whole equation into one line. So let's just review how we would put KL over R into one of our cells. So we would start off by clicking in the actual cell itself, using the equal sign to put it into the mode of programming that cell. And then we're going to start with our variables. So we're going to do the top line first, where we're going to have K times L, parentheses around both, separated as the top line, divided by R. Now remember, this is not a radius, this is radius of gyration. This is going to be the direction for which that's going to buckle or be weaker in if it's a non-symmetrical cross section. So K is going to be a cell input. L, the length, is going to be a cell input, and our radius of gyration is going to be a cell input. Now, we may not be given the radius of gyration, so we might have to calculate this. So the calculation for radius of gyration is directly below. And so we can also input that in as another cell location. Now you'll notice here that this is the square root of. So to do a square root, let's first write our top line, which is going to be the moment of inertia, I, divided by A, which is the area, put a parentheses around the whole thing, and instead of, we have to take it to the square root. So we're going to take it to the 1/2 power, or actually I should put it to the 0.5 power, the decimal equivalent. Okay, so let's look at our spreadsheet. See, this small. And you'll notice here that we have each one of these as an input. So on the top, our first input is going to be our K value. Our K value is dependent on the end conditions. Down below, I have a reference from the page in the textbook. So if we have pinned ends, that K factor is a 1. If we have free, or if one free end and the other fixed, it's going to be 2. If we have fixed on both ends, it's 0.5. and pinned and then fixed on the other end is going to be 0.7. So right now, we are just going to put one of those in. So I'm going to put the number 1 in there for a K factor of 1 pinned on both ends. Then the next thing we're going to do is we're going to put a length in place here. So we need it in inches. Notice on the right-hand side, we have the units in inches. So let's say we're looking at something that's 20 feet long. So if it's 20 feet long times 12, that's going to be 240 inches long. Now, radius of gyration, we're going to input a value here. So I'm just going to put in 1.5. And it's going to calculate my slenderness ratio. So notice here that it populated my slenderness ratio with 1.6, or I'm sorry, 160. Now that number is greater than 100. So that means that it's going to qualify for an Euler's column or a long column. So then I would go to my second tab here. My second tab is going to be the equations that are related to Euler's equation or Euler's columns. Now, as we look back, we know that we have to calculate what the critical stress is. The critical stress has to be less than the stress at the proportional limit of that material because we do not want to stress it beyond the yield point. Now, once we have that in place, then we can calculate the critical load, which is then going to be based on the factor of safety, which is then going to give us the allowable load. So our inputs here for our critical stress are going to come from the equation for critical stress, which is in our handout, back in our handout again, on that second page just below the slenderness ratio. So my critical stress equation is going to have pi squared times the modulus of elasticity divided by this whole thing is the slenderness ratio squared, okay? I also want to input what my proportional limit stress is so that I have that as a reference, and that's usually given in a problem. So up here, stress at the proportional limit, I'm going to use the number 36,000, which is typical for steel. The next one here is modulus of elasticity. This is either going to be 29 or 30 times 10 to the 6th. So I'm going to put in 29 with 6 zeros. Cross-sectional area, now this is going to be dependent on the item that we're dealing with. So I'm just going to put in 15. And then factor of safety. This will usually be given in the problem, but I'm going to put a factor of safety of 2. So you'll notice that it automatically calculated for me a critical stress. This critical stress down here is 11,179. This is less than the stress at the proportional limit, so this is good. So now I programmed my spreadsheet so that I would have to input this below because I don't want to use that critical stress for my critical load unless it meets the qualifier that it's less than the stress at the proportional limit. So once I know that, then I can manually put it in. So I'm going to put 11,179.75 down below. Now it finishes up and it calculates the critical load for me and then the allowable load. Now, this critical load is based on taking that critical stress and multiplying it by the area, the cross-sectional area, to get that critical load. Now, you might be wondering, how did I get my tabs at the bottom here? I'm going to go to a clean a clean Excel. So this is a blank sheet, like it would be just normal. So when I pull it up, you'll notice that it just starts with one tab at the bottom called Sheet 1. To rename that tab, we simply double click on it, and now you're in a text editing mode. So I can just hit the back button, the delete button, and I can put in here slenderness ratio, okay? And I can hit enter, and now it's got a new title on that tab. Now, if I want to add a tab, another sheet to this, so this is the first sheet, I want to add a sheet to it, you'll notice the plus sign next to it. I simply add another sheet. Now this is automatically called Sheet 2. I can double click on it, and I can now rename that tab. And that's what I use then, so Euler's column, okay? And then enter, and so on. And so as I look back at my spreadsheet, you'll notice that that's how I have the tabs in at the bottom. If I wanted to add another one, I have then the plus sign where I could add another one if I wanted to. Okay, so that's my Euler's column. Now, something I want to point out that I didn't say as we were going through. I didn't have to put in my slenderness ratio here as a separate option because if I click on this cell, you'll notice up here that it's actually formulated to grab the cell from the slenderness ratio sheet, okay, which was on a different sheet. So to do that, I'm going to show you the format here. So if I click on this, this is going to be equal sign, and then it has a little asterisk, not an asterisk, but an apostrophe sign. Then it has slenderness ratio, which is the name of the tab or the sheet that this is from. Then it's another apostrophe, and then it has a exclamation point, and then the cell designation. So if I would put it in another cell over here, I would say equal to, it has the apostrophe, slenderness, space, ratio, the exact title of my sheet, and then I'm going to add my apostrophe back in, and then what it needs to do is I need to put an exclamation point, C8, okay? C8 is the cell that the slenderness ratio is on that slenderness ratio page. So you'll notice that it's C and then 8 is that call out. Now, no matter what I change this to, so for instance, if I change my end condition to fix or free and fixed, it goes to 2, that goes up to 320, it automatically updates 320 on my next sheet here, okay? So as I worked towards then my intermediate, I also needed a slenderness ratio there. And notice that it populated automatically here under my inputs. Same thing on the last sheet, which is the machine design. Okay. Now, to finish up this spreadsheet, then you're going to add tabs to the bottom. Okay. And you are going to use your column assignments as your inputs. So if we open up and we look at chapter 17, let me just find a good example for us. And we look at example 17.1, okay? Example 17.1 is going to be a good example for us to use, and we'll kind of walk through this process with it. So I'm going to clear out on my slenderness ratio page, and then also on my Euler's page, anything that I had input from that previous problem. Now, be careful not to get rid of the slenderness ratio here, otherwise you'll have to reprogram it back in. So I'm going to start here with the input from example 17.1. For this problem, we have a W14 by 74 steel column. It has a length of 35 feet. It has a proportional limit of 33,000 and factor of safety of 2 and a modulus of elasticity of 29 times 10 to the 6th. What they want us to do is they want us to determine the allowable load when the ends of the column are pinned, when one end is pinned and fixed and the other ends are fixed. You may remember this from when we did it in class. So what I'm going to do is my end conditions for part A here, my K factor, it's going to be pinned on both ends. I'm going to put number 1. My length needs to be in inches here. So my length, if it's 35 feet, I need to multiply that by 12, and that's going to be 420 inches. Now, radius of gyration, we find this from the back of the book. Remember, we're going to look in the back for a W14 by 74. We already did this. And then there's going to be 2 radiuses of gyration. We pick the smaller of the 2, which in this case is 2.48. Now, it calculated the slenderness ratio to be 169, greater than 100, so it's going to be an Euler's column. Notice it's 169 populated on the second sheet. So now I'm going to input the information from the problem, 33,000 was our proportional limit stress. 29 times 10 to the 6th is our modulus of elasticity. Cross-sectional area would be gotten from the back of the book in the appendix for the W14 by 74, so that's 21.8. And then my factor of safety here is 2, given in the problem. So you'll notice here that my critical stress came out to be 9,979, which is less than the 33,000. So now I can input it below, 9,978.77, enter. And now it calculates my critical load and my allowable load. Remember, the critical load is going to be the load in which it is going to be on the verge of buckling. Buckling is is going to be considered a failure mode. And so we don't want to actually go all the way up to that critical load, and that's why we apply a factor of safety. So we're going to say we only want to go half of that, and that's what the allowable load is. So critical load is PC, allowable load is like PA. Now, let's say we wanted to do one of the intermediate columns, okay? Now, that means that our slenderness ratio has to be equal to or less than 100. Now, if we look at one of the examples that you did for your problem, what we can do is, I'm going to do number 11, 1711. It says we want to determine the axial compressive load in a steel tube that has an outside diameter of 3 inches, a wall thickness of 0.3, and a length of 4 feet, okay? So they're telling us here that our ends are pinned. I think that's what we have to assume. So our K factor is going to be 1. Our length in this case is going to be 4 feet, so 48 inches. And our radius of gyration, we actually need to calculate that. So I'm going to get rid of it here. And we are going to go to MD solids. Now I just need to find my MD solids on here. Here it is, MD solids. And we're going to go into the section properties area. So I'm going to click on section properties, simple, and I'm going to have a cylinder, pipe, or a tube. So my outside diameter is 3 inches. My inches is over here as my units. And now they give us a wall thickness of 0.3. That's going to be 0.3 on this side, 0.3 on that side, so we subtract off 0.6. So this is going to be 2.4, and then compute. Now over here, when it computes, we're going to have a radius of gyration, RZ, and that's going to be 0.9605. That's going to be the number that I'm going to put into here, 0.9605. Okay, so now you'll notice that we have a slenderness ratio only of 50. Well, that's much less than 100. Now, based on what we have here, the information that's given, we're given a factor of safety of 3, and so that's going to be a machine design situation, okay? So here, I'm going to put in my modulus of elasticity, 30 times 10 to the 6th. Yield strength in this case is 42,000. And then you'll notice here that we have a cross-sectional area. I'm going to go back to my MD solids to find the area, which is 2.5447. And my factor of safety of 3. And here it calculated for me my column constant, my allowable stress, and then my allowable load. Now, column constant. We need to populate this cell with the equation for the column constant. So where do we get that from? That column constant equation comes from the handout. So if we go to the 5th page of that column handout, see here, oh, there it is, okay. We are going to find the equation for the column constant. Now, the column constant is the same calculation for both a structural steel column and for machine design. So this is actually not just for the structural steel. It might give that impression because it's here, but the equation for column constant will be as we see it here. Now, I will rewrite it in Excel. We have to get it all in one line. So as we look here, when we input into our cell here, we're going to click on the cell, and we're going to start with that equal sign to put it in a function mode. We're going to do the top line here first, 2 times pi. Now remember, we're going to use 3.1415. Now we need to square that value, so we need to put parentheses around it to the second power, okay? And then we're going to multiply that by the modulus of elasticity. So that's going to be E. It's going to be a cell designation that we put in place, okay? Now, we're going to put parentheses around this top line, and we're going to divide it by the yield strength, okay? So I'm going to put in here my symbol right here, but this is going to be a cell designation as well. Now, after I'm done with that, I'm going to put parentheses around the whole thing, okay? Because I need to take this to the 0.5 power, because I need to take the square root. And that's how I'm going to input it into Excel. So if I go back to Excel, that is what you're going to see on this top line here. The modulus of elasticity is my top value right here. So that's going to be a cell designation. My yield strength is going to be a cell designation, okay, for that column constant. So the C4, modulus of elasticity, and the C5, the yield strength of the material. Now, allowable stress. The allowable stress is going to be based on, let's see here. It's going to be based on the top equation here. So as we look at the allowable stress, we go down to the bottom for machine design on our handout, and we are going to be using this equation right here for this particular problem, okay? So I am going to, as a challenge for you, have you put this into Excel, okay? So remember, order of operations and putting it all in one line. If you have any questions, you can always let me know, but I want you to work on this one. This one's a little bit more challenging. Remember, this part right here is your slenderness ratio. You already have that. So that's going to be a cell designation. You don't need to put this in as KL over R. This is your slenderness ratio. That's a cell designation that you'll square, okay? So you can do this. I want you to practice. I want you to kind of take this as a little bit of a challenge to put into the cell right here. So it's going to be equal sign. It's kind of long here, okay? But you have everything that you need to do that. Now, once you have your allowable stress, your allowable load is simply going to be multiplying the allowable stress by the area, okay, from up here. Because as we know, stress is always equal to force divided by area. So our allowable load is the force, so we're going to take that stress times the area. Now, if you end up on a structural steel problem, which would be problem 1710, which was one of your homework problems, then you need to create the spreadsheet for the structural steel. So you can reference that slenderness ratio by going back to that first sheet and using that C8 cell. That way it's going to populate this each time or anytime that slenderness ratio is going to change. And then here you're going to input your modulus of elasticity, your yield strength, and your area. And then you're going to get your column constant. You have to also calculate your factor of safety, and then your allowable stress and your allowable load. Now these equations are going to be found on that handout as well, but in the structural steel area. So it's going to be after that column constant, it's these two equations right here. And then as we know, allowable load is going to be equal to the allowable stress times the area. So here too, you'll notice that you have a column constant and a slenderness ratio. These are already calculated for you, so these are going to be cell references. You don't have to re-put in the whole equation again for each one of those. Same thing here and here and here and here. So it's a little simpler than what it looks like just at a glance. So let's peek one more time back at this one. Oopsie. Okay. So your column spreadsheet is going to include, the first sheet is going to be slenderness ratio. Okay. Then once you determine the number for the slenderness ratio, you're then going to have an Euler columns sheet, an intermediate structural steel sheet, and an intermediate machine design sheet. Okay, all on one so that you can do any type of column problem that we presented in chapter 17. So please attempt to get a start on this. Make sure that you add some formatting, coloring, boxes around things. Make it a pretty spreadsheet, something that looks appealing and easy and fun to use. And then make sure that you are going to save it to your drive at school, so on your network drive, so that I can get at it through your student ID number. If you have any questions, please feel free to contact me or talk to me if you see me in class.